So hello everyone, in today's session we will learn what exactly is this particular instruction, which is LDR Rd equal to constant. As you can know from the heading, we already can understand that this is a pseudo instruction. We will know what is a pseudo instruction and we'll discuss this particular pseudo instruction in detail. Okay. Very first thing that we notice here is not an actual hardware instruction. Okay, so that clearly means this particular instruction shown here, okay, is not actual hardware instruction. Okay, but this is instead converted into valid ARM instructions by the assembler. Okay, so why all this conversion is required, we'll understand it further in the next slides. See, I think in the code you will see this particular instruction very often. Okay, if you write LDR R1 comma equal to 0x ABCD1 to EF, it means load this particular hexadecimal value into register R1. So R1 value will be ABCD1 to EF. Okay, in this particular case, what will be the value of R1? This is a decimal number. So in the register window, okay, you will see the hexadecimal value of this particular decimal value 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's why I have not added 0x here. In this particular case, what happens is label. What exactly is label? In the code, we always see something like start followed by actual code written here, or something like value followed by DCD 0x123 and all such things. So these are nothing but labels. Labels are user defined names for specific memory location. If you want to mark a particular memory location by some name, okay, then you will use a label. Okay, so here what happens is now this value actually will be pointing at some memory location. Let me assume it is something like this. Then this value will be loaded into register R1. Yes. Now we understood whatever values are here, they'll be directly loaded into register R1. If it is a label, then memory address pointed by it will be loaded into R1. But doesn't move also perform something similar? If you write move R1 comma hash 0x, and let's assume we have taken same number A, B, C, D, 1, 2, E, F. Is this possible or not possible? If you actually check, this will not be possible, but move will be able to load lot of different varieties of numbers into R1 instruction. There is a condition. The only case when a value or a constant, okay, now if you write some constant here, okay, this value will be loaded into R1 only if it satisfies one main condition shown here. Okay, so what is this condition? If you see ROR, it is nothing but rotate right. IMM8 here represents immediate 8-bit value 2 into the number of rotation to be carried out. Okay, let's see what it is with the example given here. Okay, let me tell you in advance, this particular instruction will be executed if you write it in Keil. Okay, why will this get executed? Because I can write it in this particular format. What is this format? I can convert it into an 8-bit value. Is 40 an 8-bit value? Yes, it is an 8-bit value. Let me write it. This is the first thing. Next, can I rotate it some even number of times so that I can obtain my actual value? Can I do that? How many times should I rotate it right so that I can get this as the answer? Actually it is 2 into 4, 8 times. Okay, if I have to show it, then this is my initial value, this is bit number 6. I want to shift this, okay, actually rotate it here and place it in this particular position. Which position exactly? I want it here. This is the answer I want, that is 4 0 0 0 0 0 and 0 0, and my initial value is 0 0 0 0 0 0 4 and 0. How many times I have to rotate it? See, this will be my first rotation, second, third, fourth, fifth, sixth, seventh and eighth. If I rotate this value by 8-bit positions, then I will obtain the desired value. Okay, so does it satisfy this condition? Yes. I have an 8-bit value which is hexadecimal 40, which I can rotate 2 into 4 times to generate the desired constant, which is 4 and all zeros. Because this is possible, I can move this content using this particular instruction. But what if I have a number which cannot be, rotated in this particular manner, or which cannot be put into an 8-bit value and then rotated? Okay, in that particular case, that will be the next example, that in this instruction won't be executed here, and you will get one error message which states that this cannot be represented as an 8-bit immediate value. Okay, so because of which, if you want to load this value, you will have to 100% use the instruction something like this. Okay. So that will give you the answer about why exactly you need this instruction. First, to load any large 32-bit value, okay, which cannot be loaded using MOV, you will have to use this particular instruction. And even if you want to load any label directly, then you will have to use this particular instruction. Okay, but next we will learn what actually happens internally when any of this instruction is written. While explaining about pseudo instruction, I had already informed assembler in ARM converts any pseudo instruction into one or more actual instruction. So these are those actual instructions. If in case the value given here, okay, we already saw, if move operation is to be carried out, there are some conditions. If this particular constant satisfies that condition, then this will be converted into move operation itself by the assembler. But in this particular example, since this particular constant cannot be converted to a form suitable for move operation, we have to consider the next case, that is LDR. Okay, LDR instruction, we have already learnt about it in previous session. In general, if there is an instruction LDR R1 comma content of R0, what will happen here? If R0 is some address, let's assume 800, shown something like this, we already know whichever location is pointed by R0, let's assume some data 1 2 3 4 5 6 7 8, okay, that particular value is copied and pasted into R1, correct? Now how will this particular instruction work in this particular case? Okay, for that you will have to know something about literal pool. What exactly is literal pool here? Literal pool is nothing but memory itself, or a block of memory which is very close to the location where instructions are stored. Okay, this memory is created by assembler. in order to store any constants which are generated in this particular case. Okay, so let's see what exactly that means. Okay, let's focus back here. Okay, so here we have an expression wherein a very large value is to be copied to R1. While looking at this, what the assembler does is it will copy this particular value and paste it in a memory location which is very close to your instruction. Okay, and this particular memory itself is called as literal pool. Okay, assembler converts this instruction into this particular format. It will already know the location of the literal pool. Once this instruction is executed, what happens here is PC, which is program counter, it will have some address. That address will be current whatever instruction is there, its address plus 8. Okay, and offset is your additional value which should be added to this initial address to reach this particular location. That is, if literal pool address is some 1000, okay, and let's assume your initial address is some 800, that is current instruction address plus 8 is 800, then offset will be 1000 minus 800, that is 200. Okay, so once this particular instruction is executed, because this offset value is adjusted to reach this particular literal pool, okay, so now PC plus offset will be pointing on this particular location. So that particular data, which is 0x ABCD 1 2 EF, is now loaded into R1 when this particular instruction is executed. I told something like PC value will be current instruction address plus 8. Why is this the case? That is because in ARM LPC2148 that we are considering, there is 3-stage pipeline, that is fetch, decode, execute. What it means is, if there is code 1, code 2, code 3, okay, when this particular instruction is getting executed, next instruction will be decoded, that next instruction will be fetched. Okay, so it is the currently executing instruction. Okay, and since each instruction is of 32-bit size, okay, that means it in the memory, this 4 will store one particular instruction, this 4 will store next instruction, this will store next instruction, and so on. If this is the first instruction or the address, let's assume 800, but the current instruction getting executed, instruction at location 804 will be already in the decoding stage, and instruction at location 808 will be currently getting fetched, because of which PC will have current instruction address plus 8. Okay, so that's all about LDR R0, comma equal to constant. Okay, so this is how this particular pseudo instruction get converted into real ARM instructions.